Hello again, this is Bob Cox. Now I'm going to talk about noise modeling in fMRI time series regression analysis. Up until now, everything has been about modeling the signal, the pattern we're looking for. But we have to think about the noise. The noise is the enemy, and you must know the enemy. Where does noise in fMRI come from? It comes from MR thermal noise, the fact that MRI signal comes from charged particles in the body being manipulated by the magnetic fields, and there are other charged particles which are just moving around randomly because they're not frozen in liquid helium, and those also contribute MRI signal, which is just called thermal noise. That's not really very big compared to some of these other things, though. There's cardiac and respiratory cycles. In principle, you could measure these sources of noise and try to regress them out, but that is not very successful, as it turns out. It does help some, but not as much as it should. Then there are also scanner fluctuations. The hardware has thermal drift as the scan proceeds. Pulse sequence timing errors is supposed to do the same thing for every image it acquires, but of course it's just a machine, it's not perfect. Now in the last 10 years or so, I'd say that the machines have gotten a lot better, and so scanner fluctuations are generally less of a problem than they were 20 years ago. But there's also small subject head movements, things that are not even noticeable on the images really as movement, 10 to 100 microns, which is a tiny fraction of a voxel, but nevertheless it causes signal changes that look like noise. Very low frequency fluctuations, periods greater than 100 seconds. That's what the baseline model is an attempt to remove, but of course nothing is perfect in our analysis. And there's the effect called serial correlation in the noise time series. This is a statistical effect on the calculations produced by 3D Deconvolve. And then the rest of this talk will be about the AFNI program for trying to adapt to this serial correlation. Serial correlation is also called temporal correlation, that is, correlation through time. And correlation through time means that data at one point in time, the noise rather, at one point in time, can be predicted by the previous values in time. What is called white noise or uncorrelated in time noise, knowing the value of this noise at one point in time doesn't help you predict what it is in the future. But if you imagine noise that comes from, say, tiny subject head movements or the heartbeat, those things are correlated in time, the physical things of motion and cardiac. And so the noise signals they cause will also be correlated in time. Now, in the calculation of the statistics of a beta value, for example, those are done with the estimates of the noise variance. And the white noise estimate of variance is based on simply we have the data at time I, and we subtract the fitted model, the regression model, at time I, and then sum up the squares and divide by n minus the number of fit parameters. How many betas were there in the model? All the betas, nuisance betas, betas of interest. For this purpose, they're all the same. And n minus m is sometimes called the degrees of freedom, which is a somewhat opaque term in my opinion. It's basically the measurement of how many equal variance independent random variables are left after a pure noise time series is fit with some model with m regressors. It might better be called degrees of fluctuation because it's measuring how much randomness is left after you fit a model. The problem, though, is if the noise values at successive time points are correlated, which is what we're talking about here, the estimate of variance given on the previous slide is biased. It'll be too small. There aren't really n minus m independent random variables left. And so if we have too small an n minus m, that means that t and f statistics are too large. And so the significance of the activations in the individuals will be overstated. A subtler problem is that the actual variance of the beta estimate is larger than one thinks, and so beta is not as accurate as it could be. in the statistical jargon, it's not biased, but it is not optimal. So there are a couple ways one could patch this problem, both of which involve estimating the correlation structure of the noise and then doing something. The first thing would be to just adjust the statistics downward, saying, oh, well, we have this much correlation, so we said the t-value was 5, but it really should be 4. The other way is to estimate the correlation structure of the noise and then use a technique called generalized least squares instead of ordinary least squares, which adapts to the correlation structure. But of course, we don't know the correlation structure ahead of time, and so we have to both do the generalized least squares estimation and the estimation of the correlation structure of the noise, and ideally in one model. And that's a technique for that was developed in the 1970s and 80s called REML, which stands for Restricted or Reduced Maximum Likelihood. This gives better estimates for the variance, smaller variance estimates for beta, and keeps the degrees of freedom where they ought to be. And this is the technique that AFNI uses, and FSL and SPM use similar but not identical techniques. So REML is a method for estimating these variance and correlation parameters. The thing that makes it slightly computationally difficult is that estimating the correlation parameters is not a linear problem, unlike estimating the betas. But that's what the program needs to be adapted to. In AFNI, the noise correlation structure that we use is called ARM of 1-1. This is a technique, a kind of model that was developed in the 1950s, and these ARMA models are widely used in signal processing. 1-1 here means there are two parameters in each voxel. One is called the AR, or autoregressive parameter, and the other one, B, is called the moving average parameter. And A here models how fast the noise decorrelates in time. There's an exponential decay. The farther apart 2 points are in time, that's called the lag between those points, the more they'll be decorrelated. And B models the very short range correlation in time. B essentially models the white noise floor that's added to the data, and A models the long range correlations. Unlike SPM and FSL, in AFNI, every voxel gets a separate estimate of its own temporal correlation parameters. That is not a dramatic effect, but it does produce FMRI, improve FMRI reliability. A paper, which is not from our group, by Victor Olshovi, appeared in 2019 describing this. Here's what correlated noise looks like. This is just pseudo-random generated noise on the top with ARMA parameters 0.8 and 0.2, which means highly correlated in time. And you can see that it doesn't, that in any given value here, for example, we see negative values, and it's still negative for a while afterward, and then it changes. So knowing that it's negative here lets you help predict the future, not predict it perfectly, of course, but there's still fluctuations. But it does help. It does help with understanding the future. The bottom thing is the same generation procedure applied, but with A equals 0 and B equals 0, and this is called white noise. There's no correlation. Knowing that a value is negative here doesn't help you decide whether it's negative or positive there. You can have 2 negative values in a row, 3 in a row, and then bang, it's positive. So the correlation between these two, because they were generated using what's called the same random number seed, is actually pretty high, 0.5. But they'd have very different statistical properties in time, and to the eye, they're very different. And here again is the script for generating those with an AFNI program called 1D Gen ARMA 1.1. Not a very great sounding name, but at least you can download this from our website and run it. So 3D REMLFit is the program that does these calculations. Its input is the regression matrix file, which is usually in AFNI pre-computed using for the program 3D Deconvolve, which is run by AFNI ProcPy for you. The regression matrix is stored in a plain text file, so in principle, some other software could just generate it and stick it in to the program and use 3D REMLFit itself. AFNI proc pi then runs 3D RemelFit, and the inputs are these two, the in-matrix file and, of course, the data to be analyzed. And then the output data sets are structured as if they came from the older program 3D Deconvolve, the ordinary least squares program, but the statistics and betas are improved. Well, at least we hope they're improved. So here we have on the left some data calculated with the RemelFit program. On the right, some data calculating with the 3D Deconvolve program using ordinary least squares. And then I have thresholded them at a voxel-wise F value of 3.15. That's the top two panels. And we see a dramatic difference between the two. Not knowing anything about the task, but if you look at the one in the upper left corner, this certainly looks like a plausible brain map. It falls in gray matter. It is bunched up in the ways you might expect. And so this seems not unreasonable. How about that? On the other hand, this one is just like, it's got all sorts of stuff outside the brain, low intensity green stuff, just sort of scattered around, bleeding into white matter, stuff like that. This is terrible. This, of course, is single subject data. So if you imagine, though, you just take the AFNI threshold slider and just slide it up and down until you see just one or two voxels outside the brain. A crude empirical thresholding method. And you do the same on this one. On the left, in the REML, we actually have to slide it down and down until we get to F is 1.8. On the right, we have to slide it up till F is 5.3. And then if we look at these, they're pretty similar. The color here is usual in AFNI. It does not come from the statistic. It comes from the beta, which is, again, what we think is the proper thing to carry forward into a group analysis, the beta being the percent signal change caused by the Bold effect. And so these are certainly not identical, but they're very similar. This sort of L-shaped thing here with a break in it is there. This shape here is this shape here. This little red blob in the front of this one is not present in that one, but that's pretty tiny. And if you just drop the thresholds to 0 and say, here are the betas, the beta fit parameters from the REML method with generalized least squares and the ordinary least squares method on the right, again, these beta maps are not identical, but they're pretty similar. For individual activation maps, 3D RemelFit-ized, the T and F statistics are significantly different, as we saw on 2 slides ago, and they're more accurate. But at present, there aren't that many applications for individual FMRI activation maps. And for general group analysis programs, the only inputs at the higher level analysis are the beta fit parameters, the percent signal change at every voxel. And these don't actually change so much between REML and GLSQ. They do change some, and it's better to use the REML GLSQ method. But in other words, older LSQ-based group analyses are not invalidated, unlike what some people were saying 10 years ago. Here's some group analysis activation maps done with AFNI's, one of AFNI's ANOVA programs from 16 subjects, and one with the individual analysis conducted on the left with generalized least squares, REML, and the one on the right with ordinary least squares, 3D Deconvolve. And again, these are not identical maps, but you have to look very closely to find differences between these. In the future, in the near future, I hope, to extend the temporal correlation model to higher order ARMA things with more parameters. The reason for this is that when people start gathering faster data, which is happening more with more advanced imaging systems, the TRs a second or less, you can see the respiration cycles, especially in areas that border CSF, and you can see cardiac noise. And remember, most gray matter is relatively close to CSF. And the thing is that instead of the noise correlation then decaying away sort of monotonically in time as the lag grows between 2 time points, then it both decays and oscillates as the heartbeat, which of course is not perfectly regular, but it's pretty regular, comes and goes. And so the higher order ARMA models can pick up these decayed oscillation effects and compensate for them, just like the lower order ARMA 1.1 can pick up and compensate for exponential decay in time. Of course, this requires extra parameters, and doing this on all the brain in one big operation, to get use the same parameters in every voxel would certainly be relatively easy, but I personally think that's not a good idea for this, because just looking at the time series, it's clear that some voxels don't see the cardiac or respiratory cycles as much as other voxels, and so their adaptation must be done voxel-wise. And so that means need an efficient algorithm for voxel-wise estimation of these ARMA parameters. And that's what's holding me up. And if I ever get time, I will churn that out and see how it works. Thank you, and stay tuned for more.